Take 3. Okay, today we're talking about work, power, and what happens when energy is not conserved, specifically mechanical energy. How does that relate to these topics? Okay, so we've talked about work done by gravity. And that's when you're not including planet Earth in the system, right? So then gravity is considered an outside force, right? And that was not so hard because gravity is constant. It's not a changing force. We talked about work done by a spring when you're not including the spring in the system. And so then it has a very specific formula. That force changes as you stretch out, right? As the displacement changes, the force gets greater in magnitude. And so we needed calculus, and then the formula sheet gives us that formula. So that's very specific for a spring. But what about if the AP exam just gives you a certain force, like kind of vague, but it gives you a formula or a graph, okay? Then it wants you to calculate force done by that, or work done by that force. Well, I think they're going to typically give you work done like along a certain direction. So like pushing harder and harder and harder, okay, as displacement increases. That's what we see sort of on this curve here. It does flatten out. So you would need calculus. You'd either need the function f as a function of displacement x. Or you need acceleration, because acceleration and force go together. We know force equals mass times acceleration, so that's just masses wouldn't change. It would just be some number. So we have this formula on the formula sheet, okay? And it tells you to take the integral of force with respect to distance. They're using r instead of x. It's a little funny, but that's fine. So then, or you can also do the area under the graph, right? Or between the force displacement graph and the x-axis, which is what we're doing here. If you have simple things like triangles and rectangles, we can do this using geometry. And here we're going to do a little bit of estimation. So we're asked to find the rank the work done by this force, greatest to least. So if I'm looking here, I'm estimating that this triangle looks about the same as this triangle, but this is positive work and this is negative work here. They look like this cancels. I'm going to say net work is 0 joules here. For B, again, I think they're trying to make this a little bit easy on me because it looks like this triangle cancels with that one possibly. So then this is my net work. What's left is the positive square rectangle there. Okay, so I got a positive there. Here, taking a look, it looks like this triangle cancels with this one and leaves me with this skinny rectangle, okay, of negative work right there. And then last one, D, if I switch back here, it looks to me a little bit like this rectangle, triangle cancels maybe with this one, this positive one, and that leaves me with a larger negative rectangle here. So when I'm ranking these greatest to least, B comes first because it's got this big positive area of network. Then 0 is greater than negative numbers, and then I've got a small negative number for C, and then a large negative number for D. Okay. Then let's talk about power, which is 7-6. Okay. Power is related to how quickly energy is being converted or transferred. And so, and remember that energy transfer is really talking about work being done, right? So because when we talk about change in energy from one form to another, or from the system to the outside world, or the world to the system, that is work. So another way to define this is rate at which work is done. Okay. So we would say that getting work done faster in a physics sense is describing a more powerful system. Okay. So that's why, running up the stairs is considered more power, an example of greater power, than walking up the same stairs at a slower rate. And you're converting really in this situation, say like the chemical energy that's stored in like your muscles in the form of ATP into gravitational potential. And so you could consider that an energy conversion. Okay. So the formulas we have here on the formula sheet are power is equal to the first derivative of energy with respect to time. Or you can do the dot product of force and velocity, meaning you would do force times velocity times the cosine of the angle between them, right? That's a lot like the work formula we use too. Okay, so it only counts like when they're lined up together, or you take the component of the force that matches the direction here. So, and I just put the windmills on here because that's a great example of conversion from kinetic energy, right, to electrical energy. And that's a lot, and the rate at which that is done is what's generating enough power to run appliances in people's homes. So the unit for this is the watt, which is named after this white guy here. Now, unfortunately, 1 watt is not very much power. So if I like have a glass of water here and I lift it 1.5 meters in 1 second, that's 1 watt. That's not much power. So you'll often see kilowatts used. Horsepower is sometimes used from way back when. And then that, since we're talking about a rate here, energy is in joules, so it would be a joule per second or a Newton meter per second. And then we could calculate, the power as a transformation of energy, right? So if we calculate this, I'm just going to outline it. I'm not going to do the full problem here, but we can imagine we've got this woman doing a lift, okay, and increasing the potential energy in a certain amount of time. So this one I don't need calculus for, because I'm going to do basically just the simple change in energy over change in time. And in this case, the only energy I'm considering really is UG, gravitational potential. So the system is like the Earth and the barbell. And then what she's doing is she's separating the barbell from the Earth by 0.7 meters. So then I'm going to do mg delta h, right? Or delta y, however you want to think of it. And then I'm going to plug in the 13.6, 9.8, and 0.7, because all I care about here is the vertical distance, and then divided by the time that took. Okay. If she lifts this in less time, right, if the denominator is lower, less time means more power. Okay. And then again, we come back to work in chapter 8. And so the reason they're bringing this back in is because now that you've talked about law of conservation of energy, that had a stipulation. It said that mechanical energy is conserved when there are no outside forces acting on the system. Well, but, I mean, often there are. So, what then, right? Well, then we know that there's a change in energy. That the initial energy and the final energy are not going to be the same number of joules. You could start with 10 and end with 5 after some process has happened. And so, there's different ways that different textbooks look at this. I wanted to put what the College Board says in there. And they're saying that when a non-conservative force, like friction, drag force, acts on the system, then the total energy of the system is going to change. So, that's just saying the opposite of law of conservation of energy, right? Okay, so we can expect that to happen when the system is not isolated. And so, for instance, when there's friction, we know, this is why you rub your hands together, you're transforming kinetic energy, for instance, into thermal energy. And so we know friction is a non-conservative force. And so that change in kinetic becomes change in thermal, right? So your decrease in kinetic energy is going to become a rise in thermal energy. And then we could analyze that by taking a look at the force of friction times the displacement. So that's kind of a wide overview of that topic. But then when you're looking at multiple choice questions, I think you just want to check the situation, because sometimes you'll be tempted to use law of conservation of energy when it really doesn't apply. And so you want to check the system carefully. You also want to see, are they throwing in some other forms of energy that aren't kinetic, that aren't potential, right? So I like this joke. Somebody's sassy here, right? I've seen this little sticker being put next to light switches before, where somebody says, please conserve the energy, turn off the lights. And then somebody says, energy's always conserved. Well, that's true for the universe as a whole, right? We're not creating nor destroying energy in the universe. But what is the point behind that little sticker, conserve energy? Right? The point of it is that we're using electrical energy that's in the wires and transforming it into light energy, and then having the lights on when they don't need to be on is making a waste, right? And where did the energy for the electricity come from? Well, it came from the power plant. And so there's also the second law of thermodynamics, and entropy and all those things you learned in chemistry. And so wasting that energy and going into less useful forms of energy is a valid point. So yes, there is the law of conservation of energy in the universe, right? But it's going into less and less useful forms, and into higher energy bills for the school or your house. When you're looking at different situations, how did this man get his mechanical energy on his bike? Did he get it from the road? Certainly not. That didn't come from the force of friction is necessary. But where did the energy really come from? Well, it came from, that ATP, his breakfast or his ice cream cone, that stored chemical energy that he is using in his muscles to contract and to pedal that bike. So we got to be careful when we answer questions. Where